Hello and welcome to this video about modeling temperature with Newton's law of cooling. Previously we learned that Newton's law of cooling, which states that an object's temperature changes at a rate proportional to the difference between its own temperature and the surrounding temperature, results in the object's temperature being modeled by functions of the form f of t equals ab raised to the t plus c. In light of our work in section 3.3 with the natural base E, we can use Newton's law of cooling, which implies that an object's temperature is modeled by a function of the form f of t equals ae raised to the negative kt plus c for some constants a, c, and k, where k is positive. From this equation, we can determine several different characteristics of how the constants a, b, and k are connected to the behavior of f by thinking about what happens at t equals 0, at one additional value of t, and what happens as t increases without bound. In particular, this graph of y equals e raised to the negative kt shows that e raised to the negative kt tends to 0 as t increases without bound. We can also verify this by thinking of e raised to the negative kt as 1 divided by e raised to the positive kt. We know e is greater than 1 and k is positive. So if t gets bigger and bigger, kt will get bigger and bigger. And as a result, e raised to the kt also gets bigger and bigger. Finally, when 1 is divided by bigger and bigger denominators, the value of the fraction gets smaller and smaller, tending toward 0. So we've just analytically shown that e raised to the negative kt tends toward 0 as t increases without bound. Let's determine the roles of the constants a, c, and k for the function f of t equals ae raised to the negative kt plus c that models the temperature of a cooling or warming object. We know that the constant c causes a vertical shift in the graph of y equals e raised to the negative kt. And since e raised to the negative kt tends to 0 as t increases without bound, we can conclude that f of t tends to c as t increases without bound. In context, the longer an object sits in its surroundings, the closer the object's temperature is to the surrounding temperature. For example, if I leave my coffee out on the table all morning, it will eventually cool to close to room temperature. Thus, we can conclude that C represents the temperature of the object's surroundings. It's the temperature the object is going to tend towards as time goes on. Since e to the 0 equals 1, and f of 0 equals ae raised to the negative k times 0 plus c, we get a times 1 plus c, which equals a plus c. So f of 0 equals a plus c. We know when t equals 0, the output represents the initial value. Thus, the object's initial temperature is a plus c. From a different perspective, we could solve for a, and a equals f of 0 minus c. So in other words, a is the difference between the object's initial temperature and the temperature of the surroundings. Once we know the values of a and c, the value of k is determined by knowing the value of the temperature function f of t at one non-zero value of t. Let's look at an example. The leftovers from dinner are put in a 40-degree Fahrenheit refrigerator when they are 90 degrees Fahrenheit. In addition, we know that after 120 minutes, the temperature of the leftovers is 49 degrees Fahrenheit. Determine exact values of a, c, and k in the model f of t equals ae raised to the negative kt plus c. We can start by identifying the long-term behavior of the temperature. The longer the leftovers sit in the refrigerator, the closer their temperature will get to the temperature of the refrigerator, 40 degrees Fahrenheit. Thus, f of t tends toward 40 as t increases without bound. And as a result, we know that c equals 40. Next, we can use what we know about the initial temperature to find the value of a. We know f of 0 equals ae raised to the negative k0 plus c, and that simplifies to a plus c. Since c is 40, and the leftovers are initially 98 degrees Fahrenheit when put in the refrigerator, we know that 98 equals A plus 40. Solving for A, we can see that A equals 58. So lastly, we're going to use the non-zero value of t to find the value of k. In other words, we know f of 120 equals 49. Thus 49 equals 58 e raised to the negative k times 120 plus 40. Why don't you take a minute here and try to solve that equation yourself, and then we'll check back. Alright, so first we're going to subtract 40 and then divide by 58 to get 9 divided by 58 equals e raised to the negative 120k. We can use the natural logarithm to reverse the exponential function, and this gives us the natural log of 9 divided by 58 equals negative 120k. And dividing by negative 120, the exact value of k is the natural log of 9 divided by 58, all divided by negative 120. In conclusion, the function f of t equals 58 raised to the negative natural log of 9 divided by 58, all divided by negative 120 times t plus 40 models the temperature of the leftovers as a function of time. This function could then be used to determine the temperature of the food at various times, or how long it will take the food to reach a safe temperature of, say, 40 degrees Fahrenheit, for example.